So we've talked about electron counting. We've talked about X and L type ligands as 1 and 2 electron donors, and and also importantly, talked about how we determine whether something is an X or L type ligand. Now, today's lectures are all going to focus on what I'm calling fancy ligands. And by fancy, I just mean these have more interesting bonding patterns. This is where we start to stretch our understanding of bonding in inorganic chemistry compared to what you might be comfortable with from organic chemistry. And so I'm going to start off by drawing two different copper complexes that we can talk about here. So my first complex is going to be a derivative of what's called bipyridine, is going to be our ligand, at least that we're looking at. Right, so that should be an aromatic on both of these, and they're connected in the middle. And that connection is going to be pretty important. And so I'm going to put a chlorine out here. And so we know that our chlorine, that's a good old X-type ligand. We've gotten some practice with that. We know it's a 1 electron donor. Comparatively, I'm going to draw another copper complex, this time with a phosphine, so triphenylphosphine. All right, and now I have this other ligand that's based on a diol. And so let's talk about what the differences between these structures are. So if I'm going to look at these ligands, the first I'm going to focus on is my bipyridine. Okay, this is often abbreviated BPY. And so if I'm going to draw this structure out, the neutral structure for bipyridine looks like this. Nitrogen, right, it makes its 3 covalent bonds and has a lone pair. So therefore, the neutral form of bipyridine would look like this, and we can see that each one of these nitrogens, right, was a 2 electron donor. So we could kind of think of this particular ligand as being a double L type. Right, a double L type ligand. And so we could abbreviate this ligand as being an L2 style ligand because there's two different bonding sites that look like L type ligands. So let's compare this to our diol, right? And if we were going to separate this molecule away from the copper and draw out our Lewis structure that's neutral, we can see that in this case, right, one of my oxygens was a single electron donor, and another oxygen was actually a 2 electron donor based on just our rules for Lewis structures. And so this looks like an X and an L type ligand. And so we could call this an XL ligand, okay? And so these are different types of ligands that have multiple bonding sites. And so this actually has a special name. So if something has multiple bonding sites, I'm just going to move these up so they're a little bit out of the way. Maybe I'll put a frame around them so we know that they are separate, right? This is what we're talking about here. So when a molecule or a ligand has multiple bonding sites, we call that a polydentate ligand. Right, and these have multiple bonding sites. Both of these are example of bidentate ligands, meaning they have 2 bonding sites. So again, this word poly just means many. Dentate, you might think dentures when you think dentate, and that actually kind of makes sense here because you could think of these ligands as biting onto our metal center, right? So polydentate means many binding sites or many sites to grab onto our metal center. And again, bidentate means 2. Tridentate, there's ligands that have 3. There's tetradentate, right? Pentadentate. There's all sorts of these different polydentate style ligands. And these have an advantage because it's very hard to remove a polydentate ligand from a transition metal center because you actually have to remove both bonds, which can be kind of tricky. And so we can start to determine these and label them as X and L type binding sites. And even though it's one big molecule, it can bind to a metal in multiple places. So that's this idea of polydentate ligands. So let's look at a few other kind of odd ligands, right? Or things that maybe we don't think of as being ligands because they don't fit our normal patterns, right? Of having a lone pair or having some electrons that we can normally see. Because again, the purpose of this lecture is to introduce some of these weird bonding types, right? And if we go back to our definition of a Lewis base, which is one way we can think about any of our ligands, right? A Lewis base was an electron donor, meaning it's a source of electrons. And so we might not think of some things as being a Lewis base. So one of the weird examples that we have for this, right, is if we imagine that we have a metal, this can actually bind to a sigma bond, right? So like a molecule of hydrogen or hydrogen gas, right, this here is a sigma bond. And a sigma bond, right, this means that there are two electrons in this sigma bond. We're going to talk more about molecular orbital theory next week. So we'll kind of get back into this, but any of these covalent bonds have electrons. And if they have electrons, we can have some kind of an interaction between a metal and these bonds. So even though the hydrogen gas itself might not look like it would be a ligand, the electrons that are in this sigma bond can coordinate to a metal center, right? So these can be two electron donors, right? So this makes these L-type ligands, right? And really anytime that we have two electrons, they can serve as a ligand to a metal. So we could draw out a complex, right? I can write it out here. So we have a molybdenum complex with 3 carbonyls on it, 2 cyclohexyl phosphines, and an H2, right? One of these hydrogen gas molecules. And so if we're going to piece this together, right, I can see I have a coordination number of 6. I have 6 different ligands. So this is going to be an octahedral complex. Again, octahedral complexes are going to be kind of the most common thing that we make or talk about in this course. I don't have any indication about the orientation, right, of these different ligands with the way that I've drawn it out. So for as far as electron counting goes, it does not matter the isomer that I draw for this molecule. And then this last site being my H2, I'll leave it in pink so we can see it a little bit better. I'm attached just to that sigma bond, right? And this is just a 2 electron donor. So if we were going to go through and do our electron counting, right, our molybdenum brings with it, if we look at our periodic table, 6 electrons, right? We know that our phosphines are each 2 electron donors. So we have 2 times 2 electrons there. Our carbonyls, we've seen these a number of times now, right? These good old carbon monoxide ligands. We know that each of these is a 2 electron donor as well. And lastly now we have H2, which is a 2 electron donor. And so now let's make sure and see that I can actually do math here. So that should be 10, 16, 18 electrons, right? So we're getting back to that nice 18 electron guideline. The molybdenum here, there are no X-type ligands. There is no charge on the overall complex, so it's molybdenum 0, which would also be a D6 metal, right? So if we're going to go ahead and do our electron counting, we can now see that even sigma bonds, right? Even sigma bonds can be used as ligands when we're talking about metal complexes, right? When we talk about metal complexes, we can even use sigma bonds. So here's our 2 new types of fancy ligands that I've introduced here. First was polydentate ligands, right? So ligands that have multiple binding sites. And the second kind of odd ligand here is what we call sigma complexes, right? Sigma complexes. And sigma complexes are ligands that use sigma bonds to bind to the metal center. And so these are our first 2 types of fancy ligands that we have to work with that might look a little bit different than what we would expect from our organic bonding patterns.